Special right triangles are triangles that we use a lot in mathematics in a variety of situations. In this class, we will use them in area and volume and also in trigonometry. The first special right triangle comes from a square. What they did was call each side 1. Drawing in the diagonal of the square creates a triangle that is isosceles, making these two angles equal. And since the corner is 90 degrees, there's only 90 degrees left in the triangle. And since it's isosceles, each one of these has to be 45 degrees. So the triangle we're looking at that is a special right triangle is a 45, 45, 90. What we need to do is find the hypotenuse. Let's call this C. We know that a squared plus b squared equals c squared. 1 squared plus 1 squared equals c squared. That's 1 plus 1 equals c squared, or 2 equals c squared. Taking the square root of both sides, flip it around, we see that c is the square root of 2. The sides you need to remember then are 1, 1, and the square root of 2, or radical 2. Notice again that it's isosceles, that's why it's 1 and 1. And remember that the hypotenuse is the square root of 2. The way we use a special right triangle is we think of every other right triangle with the same angles, in this case a 45, 45, 90, is really just a multiple of that original triangle. For example, if this side was 5, I can see that to get from 1 to 5, I'd multiply by 5, which means this side would be 5, and the root 2 would become, on the hypotenuse, 5 root 2. So instead of 1, 1 in root 2, we'd have 5, 5 in root 2. If this side was 8, we can see that we multiply 1 by 8 to get 8. So we take the other 1 times 8 to know that that's 8. And the root 2 on the hypotenuse becomes 8 root 2. So again, instead of 1, 1 in root 2, we have 8, 8, and 8 root 2. If the hypotenuse of our other triangle was root 10, for root 2 to become root 10, we multiply by root 5, because root 2 times root 5 is root 10. That means we multiply every side by root 5, and the 1 becomes 1 root 5, or just root 5. And this side becomes, again, multiply by root 5, 1 root 5. You don't need to put the 1. What we need to do then to make this easy is find our multiplier. In the example we just did, it was root 5. We're going to call our multiplier t. And when we find it, when we find what t is, all we do is multiply every side by that t. So instead of 1, 1 in root 2, we're going to think of them as variables. Our multiplier is t, and these sides are now going to become 1t, 1t, and t root 2. And once we know what t is, for example, if it's 5, it'll be 5, 5, and 5 root 2. If it's going to be 11, it'll be 11, 11, and 11 root 2. We don't need the 1s, so we'll get rid of them. If the hypotenuse in our other triangle was, say, 2 root 10, all we need to do is take these two sides and make an equation. We know they correspond. We need to find the multiplier, what t would be, that when I multiply it by root 2, it becomes 2 root 10. We can solve this. We can divide both sides by root 2, and t will equal root 2 and root 10. 2 goes into 10 5 times. These are both roots, so you can divide them. Remember, you can't divide an integer or a whole number with a root. They've both got to be roots, or both got to be whole numbers or integers. So 2 root 10 divided by root 2 then is 2 root 5. And once I know that t is root 5, my sides become t and t, 2 root 5, 2 root 5, and then if I take and plug in 2 root 5 times root 2, notice that it is 2 root 10 that I started with. These equations can become rather messy, and that's why at the beginning of this assignment, we're going to review square roots. The second special right triangle comes from an equilateral triangle. Every side here is equal, including this one right here. What they did was call each side 2. The reason they called it 2 is since it's equilateral, that makes this piece 1 and this piece 1, so that every side is 2. Let's call this A, and we can use Pythagorean Theorem to find it. We know that A squared plus B squared equals C squared, where C is the hypotenuse. A squared plus 1 squared equals 2 squared. That's A squared plus 1 equals 4. Subtract 1 from each side, and A squared will equal 3. Square root both sides, and A is the square root of 3. Reminder that every angle in an equilateral triangle is 60 degrees. So these two then are 30 degrees because the two triangles are congruent, side, side, side. Our special right triangle is a 30, 60, 90. Just like with the 45, 45, 90 triangle, we're going to think of every other 30, 60, 90 triangle as a multiplier of the sides 1, 2, and root 3. And you do have to notice where they're located. The height of the equilateral triangle was root 3. The shortest side that was half of the hypotenuse was 1. And the hypotenuse was 2. It was twice the side that's between the 90 and the 60. Every other 30, 60, 90 triangle is going to be a multiplier of this triangle. And if the hypotenuse was, say, 12, I can see that I multiply by 6 to make the 2 12, and I'll multiply every side by 6. So root 3 between the 30 and the 90 will become times 6, 6 root 3, and the 1 times 6 will be 6. To make this easier, just like we did with the 45, 45, 90, we're going to call that multiplier t. We'll multiply every side by t. All I need to do then is set up an equation and find that multiplier, the t, that makes each side. If, for example, between the 90 and the 30, there was a 2 root 15, I would then take the corresponding sides and make an equation. T root 3 equals 2 root 15. Solve for t. Since there's multiply here, I'll divide both sides by root 3. And t will equal 2 root 5 because root 3 goes into root 15 5 times. So our multiplier is 2 root 5. That means I'm going to take 2 times 2 root 5 to find the hypotenuse. That would be 4 root 5. Between the 90 and the 60 is t, and I know that t is 2 root 5, so this is 2 root 5, and I found all three sides in the triangle. Again, I'm going to point out the mathematics can be messy on this, and you need practice with roots. So you need to hang in there, ask questions, and watch the examples in the video. Here are some questions from your assignment. The secret of working with square roots is knowing your perfect squares. Perfect square is any number times itself. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169. That's 13 times 13. 14 times 14 is 196, and on they go. These are the numbers you need to recognize. You need to find one of these numbers. 1 isn't very useful. The square root of 1 is 1, but it doesn't help us simplify a root. You need to find one of these numbers that divides evenly into the number under your square root. Find the largest. If you don't find the largest, you may have to take multiple steps to get there. In this case, it's 25. I can rewrite 75 is 25 times 3. Again, notice 25 is my perfect square. It has to be on this list. 75 is 25 times 3. I can take the square root of 25. It goes out front. You're going to take the square root when you take it out front, and it is 5 root 3. A square root is not simplified until every perfect square is out of the root. So if you solved this question and it ended up with, say, 5 root 8, you know you're not done because there would still be a 4 and 8. And you would have said, all right, 8 is 4 times 2. The square root of 4 is 2, and I'll take that out front. And there's times right there. And my answer then would have been 10 root. And this would still be under the root because I can't take the square root of 2, 10 root 2. Watch for that. The correct answer on this question is right here, 5 root 3. On question 2, 16 root 12, the largest perfect square that divides evenly into 12, it has to be a perfect square, is 4. I'll rewrite 16 root 12 is 16 root 4 times 3. I can't take the square root of 3, but I can 4. When I take it out front, I know there's times right here. The square root of 4 is 2, so the 2 goes out, and I multiply, and it becomes 32 root 3, or 32 radical 3. You can multiply a root by a root. Root 2 times root 3 is, in fact, root 6. It works. You can't add root 2 and root 3 unless you approximate, because they're not like terms. We'll talk about that later. But you can multiply them. But keep in mind, if there were numbers in front, like 5 root 2 times 7 root 3, there's times everywhere. This is 5 times root 2 times 7 times root 3. I can multiply my whole numbers, or integers if they're negative. 7 times 5 would have been 35, and I can multiply my roots. Root 2 times root 3 is root 6, and that's the way it works. Now these, in this question, are both roots. Root 3 times root 15 is in fact root 45. Now I take my list of perfect squares, 4, 9, 16, 25, and find the largest that divides evenly into 45. That would be 9. I'll rewrite 45 as 9 times 5. I can't take the square root of 5, but I can take the square root of 9. Square root of 9 is 3. Then it goes out as a 3, and I'm left with 3 root 5. 3 root 5 is the answer. On question 6, I can multiply my whole numbers because they're both whole numbers, or integers. If they were negative, that wouldn't matter. I can take 3 times 12. That's 36. I can take root 18 times root 12. 18 times 12 is root 216. Now, it's not easy to find the perfect square in 216. There are some techniques we could do to do that. We could start with prime factorization. 216. This is the hard way, but you've probably done this before. Take your prime numbers, 2 is the first prime, and divide it by 2. 216 divided by 2 is 108. Keep dividing by your primes. 2 is in 108. It's 2 times 54. 54 has still got a 2 in it. It's 2 times 27. And 27 is 3 times 9. 3 is a prime. And 9 is 3 times 3. An important thing to know is that if you multiply any two perfect squares, like 4 and 9, those are perfect squares. 4 times 9 is 36, a perfect square. If you multiply two perfect squares, you get a perfect square. 2 times 2 makes a perfect square, that's 4. 3 times 3 makes a perfect square, that's 9. So it looks like our largest perfect square is 36. What I like to do is find the GCF. This is the easy way. The greatest common factor of 18 and 12 is 6. There's a 6 in 18 and a 6 in 12. And 6 times 6 is, of course, 36, my biggest perfect square. The other way you could get that largest perfect square is to use a factor table, like I have on my website under Resources, Google Factor Table. Let's rewrite 216 as 36 times something. 36 times, using my calculator, is 6. I can see it right here. It's 2 times 3 that was left. I can take the square root of 36. The square root of 36 is 6. 6 times 36 is 216. 216 root 6. Now, that is my answer. It was a complete accident that what's in front ended up being the same that was underneath the root. Question 8 ends up being an easy one. Just remember that you can multiply an integer times an integer. They're integers because they're negative, or whole number times a whole number, and a root times a root. If I ask you to take 2 times root 3, it's the same as asking you to multiply 2 times x. You really can't do it. 2 times x is 2x. It's still 2 times x. 2 times root 3 is 2 root 3. You can't multiply them. It's still 2 times root 3. You drop the dot. So that's what's going on here. I'm going to multiply just the two whole numbers. Negative 12 times negative 13, that'll be positive, and 12 times 13 is 156. So this is 156 root 6. One of the things we do in mathematics is make sure that there's no roots in our denominator. This way our answers are all recognizable as being the same thing. There's a nicer answer for 2 divided by root 2. This is called rationalizing the denominator. The denominator, in this case, is the square root of 2. That's an irrational number. If you plug it in the calculator, it's a decimal that continues to infinity and never repeats. We're going to make it a rational number. A rational number is any number that can be written as a fraction. An irrational number can't be written as a fraction because every fraction either terminates or repeats. So we're going to eliminate the root and the denominator. The way you do that is you multiply by 1. Take your root, whatever it is, and make a 1 with it. Root 2 divided by root 2 is 1. And then multiply straight across. 2 times root 2, you can't really do that. It's 2 root 2, which is still 2 times root 2. Root 2 times root 2 is root 4. I can take the square root of 4. It's 2. And above I still have 2 root 2. Because there's times here, there has to be multiplication for this to work. I can cancel these 2's, and I end up with root 2. Remember that you need multiplication. An example is if I take 2 times 3 divided by 3, that's 6 divided by 3, which is 2. Notice if I cancel the 3's, I still get 2. That works because there's multiplication. If it was addition or subtraction, you couldn't cancel. Root 2 is our answer. Check your calculator. 2 divided by root 2 and root 2 are the same decimal. Root 2 is our preferred answer because the denominator is actually 1. We rationalize the denominator. One of the things you need to know about roots is if you have a fraction under a root, you can split it up anytime you want. This is the same thing as root 5 divided by root 2. Check it on your calculator. I'm going to rationalize the denominator. I'm going to eliminate that root in the denominator. Take your root, whatever it is. If it's root 3 or root 7, use that. Make a 1 with it. In this case, it's root 3 divided by root 3. Root 5 times root 3, you can multiply those because they're both roots. That's root 15. Root 3 times root 3 is root 9. This is root 15 divided by the square root of 9 is 3. You cannot cancel root 15 and 3. 1 is a decimal that continues to infinity. 3 does not divide evenly into that decimal. You can divide a root by a root, just like you can multiply a root by a root. You can divide a whole number or an integer by a whole number and an integer. But don't mix them. It doesn't work. This is my answer. Notice the denominator is a whole number, 3. Could be negative, so it would be an integer. The correct answer then is root 15 divided by 3. Notice the denominator again is rational. It's not a square root. 8 divided by root 12. Now some of you are going to want to multiply by root 12 over root 12, and you could do that, but you'd need to simplify it when you're done. You see, 12 has a perfect square in it of 4, so this is not simplified. Ideally, you'd like to simplify it before you rationalize the denominator. Let's take the largest perfect square out of 12. I know that 12 is 4 times 3. 4 is that largest perfect square. So this becomes 8 over the square root of 4 is 2. That goes out front. 8 over 2 root 3. Because there's times here, I can simplify. Divide by 2, I get 1. Divide by 2, I get 4. So the simplified answer so far is 4 over 1 root 3, or 4 over root 3. Now I can rationalize. Take the root, whatever it is, make a 1 with it. Root 3 over root 3. 4 times root 3 is 4 root 3. Root 3 times root 3 is root 9, and the square root of 9 will be 3. So the correct answer is 4 root 3 over 3. Again, we have one with a perfect square in the denominator. The largest perfect square in 18 is 9. It's 9 times 2. I can take the square root of 9. It's 3. So this is 9 over 3 root 2. There's times here. That allows me to cancel. I'll divide by 3. I get 1. Divide by 3. I get 3. Note that you must have division and multiplication to cancel. This is 3 over root 2. Now I can rationalize. Take your root, make a 1 with it. Root 2 over root 2. This is 3 times root 2, or 3 root 2. Root 2 times root 2 is root 4, but the square root of 4 is going to be 2. 3 root 2 over 2 is the correct answer. Now we finally get past the review. Special right triangles. This is a 45, 45, 90. We know this is 45 degrees because the three angles make 180. Remember, it's isosceles. The sides are t root 2 for the hypotenuse, and the two congruent legs are t and t. So my equation is t root 2 equals 2 root 46. Let's find our multiplier t. There's times here, so we're going to divide both sides by root 2. I can divide my root by my root. This will be t equals 2 root 23. And t are the two sides we're looking for, AJ and JF. So each one of these is 2 root 23 because they're both t. Another 45, 45, 90. The hypotenuse is t root 2, and the two legs are t and t. My equation, the corresponding sides are t root 2 equals 14 root 2. I'll divide both sides by root 2. The root 2's cancel. Anything divided by itself is 1, and 1 times 14 is 14. So this is t equals 14. So these two sides are both t, they're both 14. The two congruent legs in my 45, 45, 90 are t and t. The hypotenuse is t root 2. I can see here the corresponding sides that t is 2 root 7. That means that Fn is also t, it's 2 root 7. It's isosceles. The hypotenuse is t root 2. So the hypotenuse would be 2 root 7, that's my t, times root 2, which ends up being 2 root 14. So the hypotenuse is 2 root 14. This question will be a little messy. The hypotenuse is t root 2, and the two legs are t. It's isosceles. My equation then is t root 2 equals 84. I'll divide both sides by root 2. I'm going to need to rationalize. I don't leave a root in the denominator. I'll multiply by root 2 over root 2. So my t is 84 root 2 over root 2 times root 2 is root 4, but the square root of 4 will be 2. I'm skipping right to the 2. Now there's times here. That means I can cancel. 84 divided by 2 is 42. In other words, I'm dividing by 2, I get 1. I'm dividing by 2, I get 42. And the answer then is 42 root 2. So YE is t, which is 42 root 2, and EF is also t, which is 42 root 2. In question 23, it's a 45, 45, 90 again. The hypotenuse is t root 2, and the two legs are t. My equation, my corresponding sides are t root 2. It equals 4 root 14. I'll divide both sides by root 2. And I can divide the root and the root. That's t equals 4 root 7. And the sides I'm looking for are FE and EO, which is t. So 4 root 7, that's t, and 4 root 7 are my answers. Here's a 30, 60, 90. A little hard to remember the sides there. The hypotenuse is 2t. Remember, it was an isosceles triangle. The short leg was half. It was t. And the altitude between the 30 and the 90 was t root 3. Now you got to find a way to remember these sides and where they go. Between the 90 and the 30 is the t root 3. The shortest side between the 60 and the 90 is t, and the hypotenuse is 2t. So the corresponding sides are t root 3 equals 4/9 root 3. Well, I'll divide both sides by root 3, and the root 3's cancel, and t will be 4/9. HD is t, that's 4/9. And YD is 2 times t, 2 times 4/9. Remember, 2 is over 1. That would be 8/9. YD is 8/9. Question 25 is another 30, 60, 90. The hypotenuse is 2t. Between the 60 and the 90 is the t. It's half the hypotenuse. Between the 30 and the 90 is the t root 3. My equation then, my corresponding sides are 2t and 1/3 root 13. It's up here if you can't quite read it on the picture. Now, rather than divide both sides by 2, because I have a fraction, I'm going to multiply both sides by 1/2. That's just easier. Notice why I do that. These 2's cancel because this 2 is over 1. T will equal, I can multiply my two fractions. They're the same kind of numbers. 1/3 times 1/2 is 1/6 root 13. So XV, looks like I'm missing the box here. XV would equal 1/6 root 13. And JX is T root 3. Now that would be 1/6 root 13, that's T, times root 3. That would equal 1/6 root 39. Now I would need to make sure there are no perfect squares in 39, but notice that 3 and 13 were both primes, so there aren't going to be. So JX, or XJ, however it's written, would be 1/6 root 39. I want to point out that these answers here, that XV, which is 1/6 root 13, is the same thing as root 13 over 6. This root 13 is over 1, and if you multiply straight across, you get 1 root 13, which is root 13, and 6 times 1, which is 6. In other words, remember that root 13 is really up top. And the same thing with JX. JX, 1/6 root 39. That root 39 is over 1, and if you multiply straight across, it's root 39 over 6. So you may also enter in this way. WAMAP will not care. For question 26, our hypotenuse again is 2t. Between the 60 and the 90 is the t, and between the 90 and the 30 degree is the t root 3. Memorize those sides, you need to know them. The corresponding sides are 2t and 38 root 67. I'll divide both sides by 2. These are both whole numbers or integers, and there's times here, so I can cancel and simplify. This is 19 root 67. So AD is t, which is 19 root 67. FA, t root 3, is 19 root 67. That's my t. Remember, it's t root 3 times root 3. This would be 19 root 201. 3 is prime. 67 is also prime. I don't think there are any factors of 67 besides 1 and 67. So 19 root 201 is the answer for FA. Question 27, another 30, 60, 90. This is the short side, it's my t. This one will be easier. The hypotenuse is 2t, and between the 30 and the 90 is the t root 3. So I can see here that t corresponds with root 5 over 11. Now don't be bothered by that. It's going to be easy to do this one. Notice that this length is 2t, that's 2 times root 5 over 11. 2 times root 5 over 11 is 2 root 5 over 11. So KB is 2 root 5 over 11. KF right here is T root 3. And T, remember, is root 5 over 11. So it's root 5 over 11 times root 3. It's T times root 3. That will be root 15 over 11. Root 15 over 11 is the answer for KF. And the last example, if you made it to here, awesome job. The hypotenuse is 2t, short side is t, and between the 30 and the 90 is the t root 3. I can see that 2t corresponds with 36, so 2t equals 36. I'll divide both sides by 2, and t is 18. CR, or RC, that's t, which is 18. And RX, or XR, is t root 3, which would be 18 root 3. XR, 18 root 3. And RC is t, that's 18. You need to spend some time, memorize the 2t, t, and t root 3, where they go on the 30, 60, 90, and the 45, 45, 90, which is t, t, and t root 2. You'll be using these a lot. You got to know them.